Today's programme is brought to you by the number 6.
The Greeks were mad on the number 6. If you think of the numbers that divide into 6, it's factors. They are the numbers 1 and 2 and 3. They'll all divide evenly into 6, nothing else will. So the factors of 6 are 1, 2 and 3. Add them up, 1 plus 2 plus 3 is 6. So 6 is equal to the sum of its factors, and the Greeks called that perfect. There aren't that many perfect numbers. The next perfect number after 6 is 28. 1 plus 2 plus 4 plus 7 plus 14 is 28. The next perfect number is 496, then 8,128, and off they keep going. 6 is your first perfect number.
Maths enthusiast Adam Spencer is absolutely right. The number 6 is perfect, which makes it very special. Of the first 10,000 numbers, only 4 are perfect. As René Descartes once said, perfect numbers, like perfect men, are very rare. And maybe that's why the number 6 was revered by the ancients. Mathematician Marcus de Sotoy.
In Jewish mysticism, 6 is quite an important number, the number of days that it took to create the universe.
And I think there's almost an argument which says 6 isn't perfect because the world was created in 6 days, but the world was created in 6 days because 6 was perfect.
Absolutely. The maths comes first, and that's why nature, or God, chose these numbers, because the mathematics says that they are mystical numbers, because they have this special perfect property.
And today the number 6 still seems to resonate throughout the universe. Take a very, very close look at a grain of salt, and you will see that it is cubic, which means it has 6 faces. And of course, bees build honeycombs composed of 6-sided hexagonal cells. And take a 10-pence coin and you can place exactly 6 other coins around it. Spooky or what? And as Ian Stewart of Warwick University points out, we mustn't forget the snowflake.
The 6-sided snowflake is the classic example in the physical world. And 1611, Kepler, who wrote this wonderful little book called On the Six-Cornered Snowflake, by the time he gets to the end of the book, he's pretty much come up with the idea, well, ice must be made out of lots and lots of little particles which are all the same, and those particles must be arranged in a fairly regular way. This was long before the atomic structure of the crystal lattice of ice was discovered, and Kepler deduces this from the six-fold nature of the snowflake. It's astonishing.
I read somewhere that everybody on this planet is separated by only 6 other people. 6 degrees of separation between us and everybody else on this planet. The President of the United States, a gondolier in Venice. Fill in the names.
That was Weezer Kittredge from John Gay's play 6 Degrees of Separation. The title, 6 Degrees of Separation, relates to the so-called small world phenomenon, which claims that everyone in the world is connected to everyone else by a chain of just 6 social acquaintances. In other words, I know someone who knows 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 you. The phrase 6 degrees of separation became popular in the late 1960s, after psychologist Stanley Milgram conducted his small world experiment. Milgram asked around 300 randomly selected people around the US to send a piece of mail to a designated target person in Boston. Duncan Watts of Columbia University takes up the story.
Each of them were given a packet of information that Milgram sent to them to send to the target person, and they were given more than enough information to identify him uniquely. However, there was a catch, which was that they were not allowed to send the packet to the target unless they knew him on a first-name basis. So, assuming that you don't know the target, you have to send this packet to someone who you do know on a first-name basis, who you think is closer to the target than you are. And so that's what people did, and they passed these packets from friend to friend. And the result that everybody remembers and that became enshrined in folklore is that the average length of the chains that got to the target was about 6.
In other words, a stranger in Kansas could typically send the packet to the target in Boston by sending it via 5 other people, with each person in the chain knowing the next person in the chain. However, some scientists were sceptical about Milgram's experiment. After all, it does sound incredible that just 6 degrees of separation will connect you to the rest of the world. That's why Duncan Watts decided to repeat the experiment in 2003. But this time, he took advantage of the fact that we live in the electronic age.
By using the internet and email, we were able to perform the same kind of experiment, very analogous to Milgram's, but on a global scale. So instead of one target, we had 18 different targets, scattered as best we could around the world. And then we had sort of an open enrollment process where people who were interested in the experiment could visit our website and sign up for it and participate, and they would be given a random target, and then they had to do what Milgram subjects had to do, which is pass a message to a friend of theirs who they thought was closer. We, instead of having 300 chains trying to reach our targets, we had about 21,000 chains.
What was your average chain length?
It's about 6, surprisingly. But the real sort of mystery is how people actually do it, and furthermore, how they do it without seeming to require a great deal of effort. There's something about the nature of social networks, the way that we connect to each other, that enables us to navigate these networks even though we only have a very, very tiny amount of information about them.
So how is it possible that we're all so closely connected? Mathematicians have tried to analyse the phenomenon by drawing diagrams that show the way that we're all connected to each other, the resulting pattern being called a network or graph. Marcus de Sotoy again.
Mathematicians were trying to understand what sort of graphs have this property of 6 degrees of separation. If you take graphs where there's a lot of local connections, which is like our social network, the people who we live around, we know a lot of them around us, but a few of us know somebody across the other side of the world. So these graphs have the shape that there are a lot of local connections within the graph and a few large global connections connecting up the small local networks. And these sort of graphs have this property that you can get from one place in the graph to another place in the graph just by making 6 moves.
A biologist friend of mine was explaining to our head of department that, there were very few steps between you and anybody else on the planet. And the head of department said, "Oh, rubbish. I mean, how many steps are there between you and a Mongolian yak herder?" And my friend said, 1. The person in the office next to mine is an ecologist who is currently working in Mongolia with the yak herders.
It's a small world.
It is a small world.
I find that tremendously comforting, that we're so close. How every person is a new door opening up into other worlds.
But the idea of 6 degrees of separation and connectivity goes beyond just social networks. Connectivity helps to explain how messages get sent around our brain. It has something to say about the best way to arrange the power grids or airline routings. And you can apply 6 degrees of separation to the hyperlinking of pages on the World Wide Web. However, a more trivial example of connectivity and the whole concept of 6 degrees of separation concerns the Hollywood actor Kevin Bacon, who starred in such films as Footloose and The River Wild.
A group of college students in Pennsylvania were sitting around talking about movies, and they convinced themselves that they could connect Kevin Bacon to any other actor through a chain of movies that these actors had acted in. It's a very hard game to play without a computer. You have to know an enormous amount about movies to be able to solve that problem. It's very hard to play.
So, for example, what do you reckon Barbara Windsor's Bacon number is? Well, it's only 2. You see, Babs was in Chitty Chitty Bang Bang, believe it or not, as was Phil Collins, who played a kid with a bandage on his face. Now, Phil Collins was in a film called Balto in 1995 with Kevin Bacon, and there you have it. But why is it the Kevin Bacon game as opposed to, say, the Clint Eastwood game? You see, Kevin Bacon is particularly well connected because he's appeared in lots of films, and often these films have involved large casts of actors. Now, bizarrely enough, there's a mathematical equivalent to the Kevin Bacon game, based around the late great Hungarian mathematician Paul Erdős. Mathematicians sometimes co-author research papers, and Erdős was a prolific researcher who collaborated with dozens of other mathematicians. So your Erdős number indicates your collaborative distance to Erdős.
Anyone who's worked directly with Erdős has an Erdős number of 1. Anyone who's worked with someone who's worked with Erdős has an Erdős number of 2. And a lot of mathematicians like tracing their Erdish number to see how close they were to the great man. At the same time, he was a remarkable individual, very disorganised, would often just rock up at people's houses with a suitcase which contained practically everything he owned in the world at that time, and say, I'm staying for a few days, I give you the gift of my mind.
I'm Ian Stewart, Professor of Mathematics at the University of Warwick, and my Erdish number is 3. So I wrote a paper with somebody who wrote a paper with somebody who wrote a paper with Erdos. He spent about 19 hours a day working on mathematics. I should add, we're not most of us like that. He was a real eccentric.
He was a fascinating character. He was completely helpless in many ways. I mean, he could hardly dress himself. He didn't know how to drive a car. He didn't even know how to boil water for tea, let alone make a meal. So he was very hard on the non-mathematical spouse when he showed up at your house. On the other hand, he would save people months, if not years, off their work because of his tremendous insights into mathematics.
That was Paul Hoffman, author of The Man Who Loved Only Numbers, a biography of Paul Erdish. Erdish was an extraordinary genius who made breakthroughs in several areas of mathematics.
One of my favorite areas of mathematics that he pioneered is something called Ramsey theory. And the idea is that complete disorder is impossible. I mean, if you looked up at the stars in the sky, that eventually you would find a group of stars that if you connected them, you would find a perfect pentagon, say. And Erdish would prove, like, how many points you could throw at a piece of paper such that you would always have to have a perfect pentagon. I mean, maybe it's 37 points, maybe it's 50 points. So he was always kind of finding this hidden order in things. But more than that is he turned mathematics into a social occasion. By going around the world, being a mathematical pollinator, as it were, he'd put people in touch with each other. And he would let nothing stop him in the pursuit of mathematical truth.
So we've heard about actors who have Bacon numbers and mathematicians who have Erdish numbers. But what about mathematical thespians who have an Erdish-Bacon number? Meet the remarkable Dave Beyer, who holds the world record for the lowest combined Erdish-Bacon number. He's a mathematician at Columbia University, so it's not surprising that he has an Erdish number of just 3. But he also has a Bacon number.
My own connection with him is through his appearance in Apollo 13 as one of the astronauts. I was the math consultant on the film A Beautiful Mind. I had a very brief speaking role at the end where I congratulate Russell Crowe in the final pen ceremony. And that is how I get a Bacon number.
What gets you from A Beautiful Mind to Apollo 13?
Various actors in Apollo 13 also appeared in A Beautiful Mind, since they're both Ron Howard films. Well, Rance Howard, for example, is in both.
So Dave Beyer was in A Beautiful Mind with Rance Howard, and Rance Howard was in Apollo 13 with Kevin Bacon. So that gives you a Bacon number of 2. So you have a combined Erdish-Bacon number of 5.
That's correct.
When did the idea hit you of combining the numbers and seeing what your combination was?
After I said the line in the film, but before the film came out. Now, the scene I was in was a fairly safe bet not to end up on the cutting room floor. So after this, I was aware both of Erdish numbers and Bacon numbers, and some of the light bulb went off because, this whole 6 degrees of separation, there's courses at Columbia University about it, for example. So I just was amused by it, and I started to look into it.
Beating Beyer's Erdish-Bacon number is going to be tough. After all, Erdish died a few years ago, so he's never going to star in a romantic comedy with Kevin Bacon and challenge Beyer's record. However, here's an interesting thought to end with. There is nothing stopping Kevin Bacon writing a mathematical paper with one of Erdish's collaborators, which could in theory give Bacon a combined Erdish-Bacon number of just 2, thereby setting a new world record.
A further 5 numbers was presented by Simon Singh, and the producer was Adrian Washbourne.